Um, Distinguished participants, expert speakers, colleagues from our partner organizations, ladies and gentlemen, good afternoon or good morning, depending on the local time in your country. On behalf of the Secretariat of the Capacity Development Program on Air Quality Management and Emission Reduction of PM 2.5 for Asian countries, I would like to welcome you for the Day 3 session of the workshop on air quality modeling module. Thank you for joining this session. I will be moderating the Day 3 session on Module 3 of the workshop. Module 3 is on air quality modeling. I hope you are all doing well. For your information, we have uploaded the PPTs of the yesterday's Module 2 session on emission inventory development on the website. Please visit the website and download the PPTs if you need them. We have already uploaded the video recording of Module 1 and Module 2 on YouTube, and links are provided to the resources materials section on website near to the respective modules. Please visit the website and watch the recordings when you have time. Today there will be 3 presentations in this module, and all presentations are likely to be ended at 4 p.m. Thailand Standard Time. Before we start the presentations today, may I request all the participants to mute your microphone and switch off your video to avoid any disturbance in the streaming of workshop proceedings, like you did yesterday and day for yesterday. Also, may I request the speakers to finish your presentations within 45 to 50 minutes, so that participants will have at least 10-15 minutes for their question and answer. Like last 2 days, participants are requested to type your questions in the Q&A box, and I will convey your questions to the speaker for the answer. If you want to ask more questions, and if the time does not permit, please send your questions to me by email. I will request the speaker to reply you later. So the first presentation of the day 3 of module 3 on air quality modeling is an overview of air quality modeling by Bhupesh Adhikari from the International Center for Integrated Mountain Development, ICMOD, Kathmandu, Nepal. Dr. Adhikari is currently working at ICMOD as Senior Air Quality Specialist. He has earned double bachelor's in economics and engineering and master's and PhD in chemical engineering, all from the universities in the US. Dr. Adhikari is working on understanding the science and mitigation aspect of air pollution in the Hindu Kush Himalayan region, using the chemical transport models in situ and satellite-based observations. Prior to ICMOD, he also worked for the AV KET2 CNR committee as their resident scientific coordinator. Dr. Adhikari also worked with Kathmandu University as an assistant professor for several years, teaching graduate and undergraduate students. Dr. Adhikari, the floor is yours.
Thank you, Dr. Verma. Just quickly, I turn on my camera so the participants see me in person and get a connect of who's speaking on the WebEx platform. So again, good morning, good afternoon, depending on where you are. and welcome to this session. Let me start my presentation, the overview presentation, and I will stop sharing my video just to preserve the bandwidth, but again, turn it back on for question and answer session. And since during the presentation it is on full screen PowerPoint mode, I may not be able to see your questions. But if you need to stop me and interject, just send text to Dr. Verma and he can stop me and I can explain things. Or else I can answer all at the end. Okay, so. Okay, so can you see my screen clearly and hear me well?
Not right now. Think
Okay, sorry, hold on.
we can
share
just see
screen.
your name.
Yeah, I'm not able to share screen.
Okay.
Why is that? Okay. Share screen.
Recording.
All right. So can you see me now? See the screen now?
Yes, we can see. Make it full. Oh yeah.
Yeah. Okay. Okay. All right. So again, welcome everyone. I'll be giving two lectures. One on air quality modeling, mostly regional scale modeling, including photochemical modeling, and another one on the applications of model as they relate to air quality management. And given the organizers have told me that most people who in this audience are related to management, so although I will touch briefly on the science side, but will be mostly an overview as it is related to management aspects. And um, modeling, especially air quality modeling, real-time 3D, three-dimensional, is such a complicated topic that it is only taught in graduate schools throughout the world. So I will try to take this complicated topic and keep it simple as an introductory lecture so that people who are coming to this session will have this broad overview of what it takes to run air quality models for air pollution management. Okay, so again, very briefly, how do we study air pollution? And once we understand different aspects of air pollution, then we can manage it or mitigate it better. Right? So the picture here is shown like we study based on in situ measurements, both ground based where you have sensors on the ground, or airborne where you're flying airplanes and taking in air pollutants. And measuring them as and when they are. We also understand air pollution from remote sensing instruments. Again, remote sensing we can do from satellite, from top looking down in Earth. And here's a picture of all these different satellites. But also we can look from the ground up, and measure columnar air pollutants. Another way we try to understand pollutant behavior is through mathematical models using, simple to supercomputers. And these are all based on the first principles, chemical chemistry and mathematics. And this is today's lecture mostly focuses on the mathematical computer-based air quality model. Okay, just to start off with, there's different language that's being used when people refer to models. And I come across many people who are quite confused in this model nomenclature. So on the very first slide, I put up, what's the difference between different terminology in terms of models. So sometimes people refer to CCM as chemistry climate model. Sometimes people talk about the GCM, general circulator model, and then sometimes people talk about CTMs. And then of course they talk about air quality modeling or air pollution modeling. So basically, the difference between these three categories here, the CCM, is, if you look at the flow, your meteorology affects your chemistry, and chemistry again feeds back to radiation, which again affects your meteorology. So it's a coupled system with chemistry and climate feedback to each other. In the GCM, your meteorology, drives your radiation, and then, again, the dynamics, and then that affects your chemistry, but the chemistry doesn't feed back to, again, radiation, and, that loop isn't closed. So it's just a general circulation model. As far as CTMs go, again, these days there are online coupled CTM, but for an offline CTM, and what I mean by offline is you run your meteorology models elsewhere. You get the met data from a separate model. You run that, use the dynamics from the meteorology model, and you run chemistry, and there is no feedback between the two. So I just wanted to put this out. Of course, there are details in these models, but for an introductory lecture, just so that you understand when people refer to CCM, GCM, or CTM. And in this lecture, we will be mostly talking about CTMs. So again, air quality models, also commonly referred to as air pollution models, also referred to as chemical transport models, right? So here in principle, we're taking meteorology fields from a different model, and then running the chemistry and getting the pollutant distribution in space and time. So when we talk about models, what is it? So in terms of 3D CTMs, they're trying to simulate the behavior of pollutants as if they are in the real world, right? So we have 3 dimensions, X, Y, Z, your horizontal, vertical, and then of course in time as well. So how complicated are these models? There are range of models, different types of models, and their complexity depends on the individual model, on how detailed physics, laws of physics that they treat, or the chemical reactions that they simulate, or the topography or geography that they simulate, of course, meteorology and emissions, to what level detail. Um, you know, Based on that, the models get very complex. And I'll get back to individual of these later in the lecture. Okay. In terms of modeling, again, the next thing that comes out is the computing capacity. And the computing capacity required, again, depends on the complexity of the model, how fast you need the answers, and how much data that you need to store, as both as input or as output. Your air quality models, again, and it's a mixture of both, maybe based on first principles, or some of the equations, because you don't have first principles or laws of physics that drive them. We have empirical or parameterized relations or equations that will run the model in the absence of first principles to solve them. There are different types of models within CTMs as well, and the differences are mostly based on the time frame that they simulate, the coordinate dimensions that they run, and the spatial scales that they simulate. And I'll explain all of these. But before we go into details of the model, why models? Why do we need models for air quality management? So as I mentioned, we study air pollution using 3 different techniques. So the strength of in situ measurements is that they measure the result is accurate. But then the problem with them is that they're accurate, but they're only measuring at certain point location or several point location, and sometimes it's difficult to understand how representative they are. What I mean by that is, like, say, if you measure a pollutant in downtown Kathmandu, does it represent all of Kathmandu or only that area or that street corner? So while it is very accurate, the issue of representativeness is there, right? In terms of in situ measurements, again, you can only measure now, or you could have only measured in the past. You cannot infer about future based on measurements because the time hasn't come, right? Another problem with in situ measurements is that they cannot independently infer about sources. What I mean by that is you can take measurements and it's high or low, but you cannot directly, based on measurements alone, say where is this high pollution coming from, or where is this clean conditions arriving, and that sort of thing. Same thing with satellite-based remote sensing. It can only do past and present condition. Most of the satellites usually only give you a columnar amount. What I mean by that is, because satellites are looking from top down, it gives you a total pollution concentration, as in, like, say, aerosol optical depth, which is a proxy for, say, particulate matter loading in the world. But it doesn't give you how much AOD there is at the surface, for example. It's usually a columnar amount. And in terms of air quality management, a lot of the times you are interested in, what's happening near the surface or at the ground level. With satellites, again, there are retrieval issues. Sometimes, there's clouds blocking. And then, sometimes it's difficult getting data on bright surfaces like, over snow cover or, desert areas. And then, of course, there are issues again with day-night retrievals. Temporal resolution, although the geostationary satellites show data throughout the day and night, the polar orbiting only passes once every certain time of the day, and so there's temporal resolution. To meet some of these deficiency, again, we run air quality models, and the main use of air quality model is to understand the roles of different meteorology and chemical drivers influencing what's being observed. Okay, example, ozone. You don't say emit ozone, but you have all these precursor gases that combine and then form ozone in the atmosphere. And you can try to understand the links between different precursor emissions to observe the ozone concentration only through models. Of course, you can measure ozone and you can detect the columnar ozone amount through satellite as well. Again, models are good in trying to link emission sources with observation because, as I'll show later, models start with emissions inventory or emission sources, and then advect it downwind, and then predict concentration at a later time or location. In terms of air quality management, models are especially good if they're evaluated and the model seems good enough or fit for purpose for management. You can look at any past episode in the past, or also for future scenarios. What is going to be, say, PM 2.5 concentration for tomorrow? Um, and then it's especially important as a decision support tool. What if, and to generate what if scenarios. For example, you can use models to say, okay, what if I make my transport in the city vehicles 50% electric? How much PM will reduce if I implement that policy? That sort of thing. So we call these what if scenarios, and models are especially good in trying to get a estimate of the reduction in pollutants using these what if scenarios. Okay, so basically, without going into too much detail in the math and all, what we're trying to do with models here is that, here's an emission at a certain location of a certain pollutant. Okay? In real world, it gets emitted into the atmosphere, and then, the wind will advect it to a different location. While it's traveling, it may change it may change into a different pollutant. And then, due to different reactions and all. And at a certain different location, it may get deposited in the ground due to dry deposition or wet removal, or tries to look at pollutant concentration, starting from emissions to an observation later in time and space. So if you look at, what do we need to kind of think about if we want to understand pollutant concentration as a function of time and space, you want to look at, the emissions, including the primary and precursors, the transport, because, pollutants are advected long distances away from its original source, whether it has any transformation in terms of reactions or phase change, or changes in size distribution, and how is it removed. So the models basically try to look at say concentration change or number density changes for aerosols as a function of the production terms, which is your emissions or chemical reactions, the loss terms, which are mostly your removal or loss from reactions, and then your transport terms with the wind. Okay, without again going into the details, this is the equation that models usually try to solve. Again, as I mentioned, there are different types of air quality models depending on what the question is at hand that you want answers for. And usually for air quality management, you'll come across different types of models. For example, a box model is something where there's no advection or like there's no flow of pollutants in and out of this box. It's mostly looking at chemical reactions, transformations in within the box. And sometimes these are good models to try to understand the process, or even you know or in during stagnant conditions, you want to look at or understand pollutant behavior, you can use a box model. Similarly, a columnar model, again, in the vertical, when you want to look at, pollutant interaction with, say, clouds, that you're only considering the vertical dimension. Two-dimensional models are, as the figure here on the bottom right shows, can be used to look at dispersion, say, of a pollutant from a smokestack, and you look at the emissions, and then based on local meteorology, how far does it go before it gets deposited in the ground, right? And then, of course, there you have your three-dimensional models, and in here, there are mostly two types. Okay, one is your Lagrangian model, and the other type is Eulerian models. Okay? And both are widely used for air quality management. And not just management, but also research and trying to understand atmospheric processes. In the Eulerian model framework, again, like I said, models are trying to replicate what happens in the real world, right? So you're trying to replicate a situation in the Eulerian one where you have Earth as different grids, or different, a city as different grids, and you have different sources within the grid, and you can have multiple grids to simulate a city or a region. And there is wind and air pollutant flowing from one grid cell to another. Here we're just showing X direction, but it can flow also in the Y direction, and again in the Z direction, right? So the coordinates are fixed, and pollutants and the meteorological drivers flow in and out of the grid cell. In a Lagrangian framework, you have these fixed air parcels where you have pollutants inside, and then because the parcel itself moves, the pollutants are not going in and out from one parcel to another, right? So whatever reaction happens here, and then the deposition and all comes within this as the parcel moves in space and time. Right. So one of the drawbacks with a Lagrangian model is that if there's a pollutant A here in this grid box, and then pollutant B here, and they could combine to form a pollutant C, that is possible in your Eulerian model, whereas it is not possible in Lagrangian scheme of models. Okay. In terms of, again, the spatial scales, and these numbers are, I guess, getting outdated every year as we advance in computing technology. But, colloquially, I mean, these are just rough estimates, and the spatial resolution can change. But global models are simulated at 100 to 500 kilometer resolution, but these days are mostly 100 and sub 100. We have models now running at 40 kilometers resolution globally as well. So, like I said, this is just a rough estimate of the resolution of the models. And global models, as the picture shows, simulates the whole globe. There are synoptic models where you can, it's run at a scale big enough to, capture these synoptic features, and are usually run 15 to 100. But again, the numbers are not absolute. They go anywhere from, a couple kilometers up to 50 kilometers scale these days. Mesoscale, again, can be anywhere from 1 to 50 kilometer resolution, and then are used to run city scale or regional scale air quality models. And micro scales are from few meters to kilometer scale, where you capture the very fine details, including, let's say, building structures and flow between buildings and that not. Also flow within canopy and that sort of thing. But for our scale, in terms of air quality management within cities or within region, we mostly focus on these mesoscale models. Again, given the audience, I have provided the reading material if people are interested in detail about running models. But in this 1 hour, we cannot really go into details. But just to get a brief overview, there's good examples of reading and also examples of the model in the Wikipedia, and it's detailed information on, say, models like WRF-GAM or CMAC, which are the widely used Eulerian type chemical transport models, and then also provides links to Lagrangian models such as high split and FlexPart, which are also used globally. Again, as I mentioned, what we're trying to do within these models is, if you look at a volume element, and again, I don't want to go into details of the math, but basically the main difference between Eulerian and Lagrangian, and I only focus on these two for air quality management because these are the models that are widely used on a city scale or mesoscale air quality management, is that in the Eulerian, as I mentioned, the advection term is there, right? Whereas in the Lagrangian model, because the air parcel itself moves, you do not have this advection terms, and you only have production and loss terms, right? And again, there are strengths and weaknesses of both Eulerian and Lagrangian models, and I guess you can read up on the differences between these two models on the source provided there, and also the reading materials submitted separately. But for now, you just want to look at, these broad two-type models used in regional and city scale air quality management. Okay, and I think this is my last slide with the math. Okay. And the reason I put this here for the Eulerian one, and this is just an example, there are other examples that will come up as you deal with models is, as I mentioned, for Eulerian, we are trying to solve this equation. Yes, and there it's a simplified form. Production, you have hundreds of chemicals and emissions from different sources, different locations, and also the production P term itself is, as you unpack, becomes very complicated. Same thing with loss. You can have loss with dry deposition, wet removal, loss due to reactions and all that. But what I'm trying to point out here is, the models, people say, oh, models are uncertain and all. One of the inherent problems with models is, yes, we can, form the problem that, you can find the concentration of any pollutant at any given time and space with this, nice looking differential equation. But then the problem is, we can formulate the problem, but the way the problem sentence or the math is defined, we do not have analytical solutions to solve this. And what it's usually done is we break this equation into the advection terms and the chemistry terms, and then assuming that these it's possible to break them. So you first solve this equation for just the advection, and then you come up with a intermediary concentration. Then you solve for the production and loss terms, and then you have the final concentration at time plus delta time. So it's forward in time, right? This is called operator splitting. And this itself, because we're solving this equation using this technique itself, sometimes can introduce errors depending on your species in condition, right? So, and again, like I said, the reason I'm bringing this issue up is, in models, because we're trying to simulate the world, and processes as it happens. There's lots of uncertainty in replicating that, but also, when you look at when you're trying to solve issues because of the analytical tools and all, the error is introduced from the very first, equation itself, right? But that doesn't mean that models are no good. These days, the concept of fit for purpose. Yes, models are uncertain. Yes, the models do not do a good job all the time. But are they fit for purpose? Do they provide useful information for air quality management? As I mentioned, there's issues with managing air pollution only with observations, and there are issues with managing air quality only based on satellite data. So we use these models to link emissions to observations and to try to understand air quality models from an air quality management perspective. You want to understand what is the data flow and what happens in the model so that you are aware of the limitations of the model as well as the strengths of the model, and you can manage your air quality related questions and problems accordingly. So here's a data flow chart of a regional CTM. Uh, Except for boundary conditions, the flow chart, the flow is same for global models as well. And in this talk, I will go into details for each of these processes. Mhm. And again, I don't go into the math, physics, and chemistry for each of these processes, just what are some of the issues, so that, as an overview talk, you try to understand how good is the model, and again, what you can do with this particular model or the model that you're using to manage your air pollution. Okay. As I mentioned, the first thing is models link emissions to observed concentration here. So to run a 3D model, of course, your pollutants are advected by weather. So it needs data on meteorological variables such as wind, temperature, and others. I'm just listing few ones here. These are not the only ones. that need to be brought into the model so that you can affect your pollutants. Because you're trying to simulate the world, as is it are they urban environment, are they lakes and rivers, are they over oceans, are there mountains? So you need surface properties again, that go into the model, right? And then to make models better these days, people use what's called satellite data assimilation. You take observations that are existing, feed it into the model, and then use that to run your model forward in time. For a regional model, you need initial and boundary conditions, and again, I will explain that in detail. So that outside your city, what is the pollutant that's coming from outside your city or region, that needs to be fed into this model for calculation. Within the model, of course, you need to understand what are the fundamental laws that the model is using, what are the chemical reactions that the model is simulating, and what are the mathematical techniques that the model is using to simulate air pollution, so that you have a better idea on the observed concentration, and use the model accordingly. And it's not just running the model. Again, there are tools and techniques on how do you interpret the model results, because it's gridded in space and time. How do you visualize behavior in 3D? How do you do spatial statistics? How do you look at time series coming off the model? Again, these are details that you have to understand to be able to use air quality models and then use them effectively for post-analysis or air quality management issues. So the next set of slides, I will go for issues related to each of these, the metrology, emissions, boundary conditions, etc. Okay. So when you're, suppose here's a region that you're trying to simulate for air pollution. So some of the issue here is, okay, you can have emissions in here, you have metrology within this box, and you have your physics, chemistry. But then sometimes there's long range transport of pollutants, from all directions, X, Y, and then Z. So how do you deal with times when pollutant is coming outside your domain? And this is what we mean by boundary conditions. For a regional model, you will need to look at boundary conditions from X, Y, and the top direction, because models do not simulate, the 3D CTMs do not simulate stratosphere or very high up in troposphere. So you want to look at pollutant transport from these. If you're looking at a global model, again, if you just start your emissions, it takes a while before these emissions are, filling up the domain, and then, you get steady state like concentration. So you want to think about spin up time, and the same thing for your regional models. If you just start your emissions at the surface, you need to run the model for enough time so that that pollutant from the surface gets advected in horizontal and vertical direction, so that you have the pollutant concentration in a way that you can actually start doing analysis. Because in the real world, pollutants are there from yesterday, day before, a couple of years ago, depending on the type. Whereas in the model, pollutant concentration only starts once you start your simulation. So you want to understand, how much spin up, we call it spin up time, how much time that you have to run the model prior before you can start using the model for analysis. Okay. So as a air quality planner or management person, you want to again look at the issues in how is it the model simulating pollution from boundaries. Usually, what's done these days is you take a global model, which is coarser resolution, and then you take the boundary from conditions from global model and feed it into a high resolution regional model. And of course, there's challenges related to interpolation in space and time. And sometimes the global model has different species than the model that you're running at a regional or city scale. So there are challenges in mapping pollutants from one model to another and that sort of thing. Again, I don't want to go into details, but these are some of the issues that as an air quality manager, you need to think about when you're running regional models. Again, I mentioned here the models need meteorology to drive pollutants, and it is not a fixed pollutant. As the simulation showed, you need meteorological variables in space and time, and there are different variables, vectors, scalars and all. So the challenge is, how do you get these meteorological variables if you're running a CTM which doesn't simulate its own weather? Where do you get the meteorology data continuous in space and time? And if you're getting it from a Corsa model, how do you interpolate to the model resolution that you use? And then in terms of meteorology, the data is available both as a forecast if you want to run air pollution forecast, or if you want to analyze a past episode, there are data available from based on observations, what's called a reanalysis. So it's model run with observations assimilated into that model. So which meteorology data are you using and need to use depends again whether you're trying to do forecast or reanalysis. And these are things that you would want to understand while you're doing air quality management. Emissions, again, the strength of the model is connecting emissions to observed concentration. But then the challenge is, if you put, garbage emissions in, you get garbage data out. And this is where the problem with models are, in that, emissions are highly uncertain, and um, the strength of the model again is, what type of emissions are you using? I'm just showing you here an example of a gridded emissions inventory that's available globally at 10-kilometer resolution. I'll show in the next slide. There's lots of emissions inventory at different resolution, different time, and the science of making emissions inventory itself is very complicated. And I think you've already listened to building emissions inventory yesterday, so I won't go into details of that. But from a modeling perspective, mainly there are two types of emissions, what we call the anthropogenic, industrial power plants and shipping and all, and then open burning. What is your uh, burning in open area that's mostly detected by satellites? So your forest fire burning, your agriculture residue burning, and your municipal garbage burning are examples of open burning. The trouble with running models without understanding your emission is, that's what leads to what people say, oh, your models are very uncertain or not good, is that, unless we understand the emissions and how that's being treated in the models, you're not going to get good predictions coming from the model, even if you have very highly complicated models based on first principles, or, highly high resolution models, like even if you're running on 1 kilometer by 1 kilometer resolution, that sort of thing. Some other issues with related to emissions are, do you have the emissions resolved by sectors, and by sectors meaning transport, or within transport also two-wheelers, four-wheelers, that sort of thing, diesel, petrol, and then do you have the sources right? What part of the city is more pollutant than, say, another part of the city? So you need to understand both the sources as well as sectors, and these are all resolved in a good emissions inventory. And I don't want to go into details because you've already heard about emissions, but you want to think about emission factors that's gone into your emissions inventory, activity rates. Does the emission provide you diurnal and seasonal variations to run in the models? And because we're running a three-dimensional model, you also want to think about, where do you place your emissions in the model? Because models have vertical layers, starting from say 10 meters above surface layer all the way up to, um, 15, 20 kilometers in the vertical. And the lowest resolution, at the lower level, your model vertical layers are very low. So you have 30, 40, 50 meters, and as you go higher up, you'll have thicker model resolution. But the injection height is important because the height where your transport emits or your residential sector emits is different from a large power plant, which has, like, say, 100-meter stack height, or say very open, very intense forest fires burning that inject pollutants couple kilometers into the atmosphere. So you want to think about how is the model treating these. And then the major other issue is emissions inventory are built for certain species, whereas your models might run a lot of different chemical mechanism, and I'll explain in a different slide coming up. But that's something also that we need to understand, whether the emission inventory species map onto the chemical reactions that the model is simulating. Again, here's a good website. This is just for your reference. I'm sure people mentioned yesterday on the emissions inventory site. If not, here's an example of all these different emissions inventory that's available globally at different space and time resolution. This is just a snapshot. There's, I think, 60 plus inventories on this site. The data is freely and openly available. Just go here and try to look at it. And there's a very easy to use interface that you can just click and look at the spatial and temporal resolution of the inventory that are used in air quality climate models. Okay, so the next thing that you want to think about in your air quality models, again, I'm not going into the physics and chemistry, but just trying to explain a bit more on the data flow of a 3D model, so that you understand what all it takes and where the model strengths and weaknesses are. So once the pollutant is injected into the atmosphere, the two ways that it gets removed, other than from reactions, are what's called dry deposition and wet deposition. Okay, so wet deposition is removal by clouds, rain, and dry deposition is when it just falls on the ground. Deposition on leaves, material surfaces, and that. So traditionally, how modelers have done deposition is that we've come up with this concept of deposition velocity. So if you have a concentration and you have a deposition velocity, then based on that you can come up with estimate how much of that pollutant gets deposited on the ground. And this is something that was developed in the 1970s, and it's been in use since then. We need better processes, and there have been some advances, but a lot of models still use the process that was developed in the 70s, and we need better information on this. And this is something that a lot of uncertainty lies in the models on how we simulate deposition. And I don't want to go into the details of the mechanism here, because this is an overview presentation. Same thing with wet deposition. Okay, it doesn't snow or rain all the time, so most of it is dry deposition. But for when times for rain and snow, hail, you want to think about how do these pollutants interact with these meteorological features, whether it's removed by washout, as in rain, or if they are soluble in clouds, and then if it is scavenged by clouds, or the term is rainout. And so you want to understand whether models actually use these processes, and if so, which process do they simulate, and what are the equations or what are the mechanisms that they use to simulate this from an air quality management perspective. Transformation, again, okay, here is another loss or a production term, depending, there's many chemicals. And here's a nice chart from Seinfeld and Pendes, the classical book on atmospheric chemistry and physics, different chemicals, their lifetimes as they on spatial scales as well as on temporal scales. So the very short-lived species are emitted and then they react within few meters, whereas the moderately long-lived live a bit longer and then are available from emissions at a wider scale. And then of course you have your long-lived species that can be transported or are present for longer time frame as well as spatial scales. So depending on the pollutant that you want to model, the resolution or the temporal and spatial resolution is um, best suited for this, and this is what the chart here is showing. But that doesn't mean you don't simulate NOx or hydroxyl radical even at, let's say, 50 or 100-kilometer scale. I mean, then you start parameterizing them and you use averaging, and so that's where the model uncertainties start to build. And on the second Y column here, uh, it also shows the processes that are governed in terms of whether it's in the boundary layer or intrahemispheric mixing, um, that sort of thing, right? So in models, you have in the real world there's thousands of chemical compounds, but models do not simulate all of these compounds. So say the master chemical mechanism out in NCAR, the National Center for Atmospheric Research in US, has let me see. I think yes, 7,100 reactions, and it's got around 2,400 species. Obviously, the models do not simulate all of these reactions, or nor do they simulate all the species. Right. So what's done is people take all these compounds and then put them as lumped species. So instead of alkane, alkene, and all, they say put hydrocarbons or aromatics. They lump it together and you form a set of reactions which are called your chemical mechanisms. Okay, and I'll come to the slide soon on that. And then based on that they come up with reaction rate data from your laboratory and studies or field studies. And then so the model can simulate a set of reactions with a reduced set of compounds. Okay. And then as mentioned here in the chart, as well as from chemical kinetics, some reactions happen in milliseconds, microseconds, and in some take longer. So how do you solve these reactions in a model? What time step do you need to use, or what sort of mathematical techniques do you need to use to solve these reaction in different schemes? For pollutants such as ozone, you want to not just look at emissions and reactions, but also photolysis, and you want to look at the schemes that models use. How do clouds affect your photolysis? So that how do aerosols impact your photolysis schemes, and whether the model that you're using uses these schemes or not. Also, in addition, there are heterogeneous reactions for certain compounds on aerosol surfaces or aqueous surfaces. So do the models treat heterogeneous chemistry? If so, how? And what sort of reactions? You want to be knowledgeable or understand these processes before you start making interpretation about your model species. And again, I don't want to go into details, but there's a lot of details on this particular slide itself, or the set of reactions or lump species that people work on. How am I doing with time, Ram? Because I'm doing the next set of slide, I can move fast or go slow as in when, because I cannot see the slide when I'm doing slide sharing. Okay. Um, Okay, anyways, moving on. Because I have both the presentation, let me just go on the pace. But please let me know if I'm going too slow or too fast. So like I said, there's thousands of compounds, a lot of reactions that are documented, but then models do not simulate all of that. And what's done is, of course, these are not the only set of reactions, but there are the most widely used reaction schemes in air quality models. And just to name a few, there's say reaction schemes that's like a carbon bond mechanism and different versions of that. There's and these are developed by different groups throughout the world and for different purposes. So, for example, the RADAM one is built to simulate the acid deposition, so it focuses on the species that are relevant for acid deposition, although it simulates a lot of gas phase and species, but was more focused for solving that, right? So here's bunch of reaction schemes, and you want to understand which of these models or the model that you're using simulates which reaction scheme, so that you get a sense of the predictive capability of your model, right? And again, there's the model that have a lot of reactions and schemes are not necessarily better models in that you want to have models that fit the purpose or answer your question, right? So it's not necessary that you need to run models at 1 kilometer or like in a few minute time step with maximum possible reaction schemes.
Dr. Adhikari,
Yeah.
sorry for interruption. Could you please wrap up your presentation?
Sure. Okay. Yeah.
Thank you.
So these schemes, I think I'm done in like maybe a few minutes. Okay. So these are mostly for gas phase species. But for aerosol, when you're trying to simulate, aerosols add another layer of, say, complexity in that, for gas phase, you don't have to worry about size or mixing state or morphology. But for aerosols, you do. And so you need to have schemes or, processes that, take into account the size, mixing state, and morphology. And I'm just listing here schemes that are available for a model WRF-CAM. Again, these schemes, both for gas phase and aerosols, are widely available in, say, CMAC or CAMAX or WRF-CAM. So these are different combinations, and within one model also, you can have different combinations of these schemes to run your model. This is why a lot of the times models are similar, but a lot of the times the models are very different because depending on which aerosol scheme, which aerosol thermodynamics that you use, or which gas phase reaction that you use, that and then which metrology that you use. If you use the right set, you may have two different models, but in a sense, they're basically same models because they're using underlying similar schemes and parameters, right? Last thing with the model again these days is that people are continuously using data assimilation techniques to improve their model. One other confusion that I find with people that I interact is a lot of people think that models are run based on observations, which is not always true. Models are run with emissions, and then taking the emissions with first principles or parameterized equation in further downwind in space and time. But to improve model resolution, yes, you can improve your emissions, you can improve metrology, you can improve processes, but then these days, because with satellite you have all these wide scale observations that you can now begin in near real time, so that you can take all these observations, feed it into the model as an initial condition, or as nudging to your model field, and then use this information to predict future air pollution. And this is called satellite data assimilation. While it improves your forecast, because you're taking observations at a certain time and then moving forward, the problem with this chemical data assimilation is now you lose your link between emissions and observations. So if you want to use the model to connect emissions to sources, you do not want to do chemical data assimilation, even if it improves your model observations when you compare with observed fields. But if you want to just use it for forecast or better prediction capability, then you need to use what's called chemical data assimilation. Again, this is a vast field. There's different types of assimilation techniques, and based on the technique, the complexity is there. But I don't want to go into details. Just read up on the source provided here. But again, there are challenges with chemical data assimilation in that you don't have data for every species, and you have limited observation, as in the shown figure here. There are data gaps, and then we have limitations on uncertainty with measurements as well as emission as well, because assimilation takes into account both the observed field as well as uncertainty, and then it takes mathematical techniques to come up with optimized field which is better than your free flowing model. This is my last slide for this talk. So for regional forecast, there's different models that are providing forecasts routinely, and AQICN has compiled the list, and you can go into this website to try to find forecasts for your area. Also recently, for South Asia, India has been providing Wolfram forecasts, and you can go into this site to look at forecasts for your model. So with that, I end my first presentation, and I'll pause here for questions.
Thank you so much, Dr. Adhikari, for your very nice presentation. It was full of very new informations. Now, may I request the participants to write the questions in the Q&A box, and then I will convey your questions to Dr. Adhikari for the answer. There is already a question from my participants. What is the best way to verify the model results?
Okay, so again, the terminology as well, because models are taking emissions, advecting, and then to a certain space and time, and then you're predicting. I think the terminology that needs to be used is evaluation. How good is your model in terms of its prediction capability? People always say we need to validate a model. Validation of a model means whether is your reaction schemes right, or is your deposition scheme right. But if you want to look at how good the model is in its ability to simulate observed behavior, you want to evaluate the model, right? So I just want to, because there's confusion in the community that I often come across people that say we want to validate the model. So you want to be careful in the sense that are you evaluating model performance, or are you validating a process within a model, right? So if your question is regarding how do you evaluate model performance, again, you can evaluate model performance with a point source or a satellite data or columnar, and you just want to be aware whether if you're comparing apples and apples, because model will give you a grid value, whereas point source is at a certain location. Of course, you can take a point location and take the grid value there and collect. But again, I mean, model evaluation is also something that you need to be careful uh, in space, time, and in the vertical, because you are simulating. So suppose your observations are over mountain region. So in your topography, does your model represent the model observation station height? Because if you're simulating 50 by 50 kilometer, even Everest, Mount Everest, which is 8,000, above 8,000 meters, in the model world will be around 5,000, 6,000 meters. Are you correctly comparing point source with, say, model grid cell. So there are issues again comparing observations, and that's a conversation that we need to have separately.
Um, what would be the main source of uncertainties to be contended in order to obtain reasonably accurate results?
Okay, so again, like I said, in the data flow, there's lots of uncertainties, right? Because what goes into the model, you know, that is where your uncertainty lies, and what happens inside the model, that's where your uncertainty lies. So you want to, if you're in a very say dynamic region in terms of metrology, you need to make sure, is your metrology good, is your emissions good. If you're in a region where, okay, metrology is calm conditions, your weather doesn't change all that much, do you have good emissions inventory, both in space time and resolved sectorally, diurnal or seasonal? Because when you make emissions inventory, maybe yesterday you talked about emissions for a day or season or annual, and what sort of emissions are you feeding into the model in space and time?
Yeah. If someone is very new in the field of regional air quality modeling, which basic models should be someone start with?
Okay, good question. And I think in my experience, and this is what I do with students that work with me as well, is that I first ask them to take already existing models and use the data from those models to interpret observations. Once you know how to interpret data coming off from an existing model, once you know how to visualize, how to do data analysis, once you start looking into that particular model and trying to figure out which chemical schemes it's using, or which what are the processes that it's simulating, you get a good sense of what it takes to run the model, what it means for the simulated fields, and then only go into running your own models. So these days, even institutes that were developing models in the past have stopped developing models and concentrated on few models, and just you focus on the application. So say, like, this is why you have few limited models in use these days, like Wolfram, CMAC, CAMAX, and people have stopped developing individual models, because like I mentioned, most of these models are using modules, as in deposition, or from different schemes or researches, and feeding that in. So I would say, learn how to extract data and interpret data from existing models, and then move on to running your own models.
Yeah, the last question, because we are running out of time. Are there South Asian specific downscaling air quality um, model that you are aware of? And what are the challenges with such link ensemble study?
Okay, so again, you need to think about models as in used for and this will come in the next talk. Models are used for a variety of applications, and I will explain that in the next presentation. But yes, if you're looking at research question or policy related, there are models that are used in South Asia, even though they were developed in Europe and North America. Again, we customize it to South Asian region, but then again, the model is trying to simulate the whole globe, right? And so there are equations that are based on, on first principles. So it doesn't really matter whether it is used for South Asia or Europe or North America. But then there are equations in the model that are parameterized and may not be accurate for South Asia. And these are things that when we implement models in Asia or South Asia, East Asia, that you want to look at, what are the processes, what are the parameterized equations, do we need to customize it for our region. So the models need to be fit for purpose. Yes, they're uncertain, but what can you say despite all the uncertainties? And I'll give examples on the next slide. Even with uncertainty of the model, how can you use these models for better air quality management? Um, yeah,
There are some questions, but we will take those questions in the next session. Since you will be the second speaker for the second presentation. So let's say a 5-minute break, and we
yeah.
can resume the session at 2:15 p.m. Bangkok time. Now it's 2:10, so just 5-minute break.
Thank you. See you soon. I'm ready, so just let me know when you are.
Yeah, we can start.
Okay.
Try to finish your presentation within 30 to 35 minutes so that we will have some questions because it's already
Sure. I think this will be easier because and can you give me warning when I'm around half hour?
yes,
Because
yes,
like I
sure.
said,
Yeah.
we can go as detailed or as quick. Um,
Okay.
yeah. Okay, so again, welcome everyone. So this is the second lecture, and I think you'll find it more useful. And I've tried to put many examples as applications for using air quality modeling for air quality management, and will not be as heavy as the first lecture, even though the first lecture I tried to stay away from the details of physics, chemistry, and math. But the second lecture is what can you do with these models? Okay, so just to recap, here's the data flow chart. This was presented earlier as well. But this is what goes into the model, and this is what you can use the model for. So you can look at using models. You can again look at how good is your emissions, or you can look at all these. How is your model affecting pollutants if you have meteorology and that sort of thing, right? So, and I'll give you examples. So the first thing that the model does is gives you a continuous pollutant distribution in the horizontal as well as vertical layer. Okay. So on your left here, is the surface layer. This is a example from WorfChem, but it can be similar for ChemX or CMAC or any other model. Even Lagrangian models. Okay. So here, and as you see on the right here, the nice thing with model is, it's not just the surface layer, which is important for your air quality, your agriculture, your human health kind of issues, but then it can also give you pollutant fields in the vertical. So here, the top one is pollution, black carbon in this case, in your 850 hectopascal model layer, which is around kilometer or so. How does the same pollutant, again, look at the color scale and the magnitude, it changes, but then, where is it in, say, mid-troposphere, around 5 kilometers above ground, and how is the pollutant distribution, say, around 12 kilometers. And it gives you the distribution for any pollutant, not just primary, but also secondary in both horizontal and vertical. Here's an example of model for temporal distribution. And you can club, if you run the model long enough, you can have, say, average for pre-monsoon or like, average for monsoon. And you can look at the differences in pollutant concentration between season. Or, not just regional like this, you can, pick a point in, like, say, for example, Mumbai here. You see this hotspot in pre-monsoon, you can, do it if you've run the model long enough, or in the time resolution that you output the data, you can look at the whole year. How is the pollutant distribution changing as per time, and also in the vertical, not just the 2D space that I just previously showed. And because you have all these cities in any given location, you can look at multiple locations, multiple cities, vertical layers, and you can look at how the pollutant is distributed in time and space. Again, the resolution here is on y-axis is your vertical. So this current model was running from above ground, and of course we simulate the whole topography within this region from sea level to mountains, and then the pollutant distribution from whatever meters or kilometers above ground layer at that layer up to 20 kilometers. So here over Himalayas, you can get 20 kilometers. So if Himalayas is 8 kilometer, you have 28. If it is, sea level, then you have 20 kilometers above sea level. And again, the vertical is important for your climate and also pollutant transport, but your horizontal distribution is important for your air quality or impacts on agriculture. And I'll come to examples of that. As I mentioned right off the bat, I mean, these were examples of model free flow without any observations assimilated, including satellite or point observations. They're free flowing models. These days, increasingly, because models are uncertain and we have all satellite data, you use satellite information with modeled information. So with clever mathematical techniques, and you come up with improved estimates. For example, in this case, PM 2.5, using both satellite data and model data. And again, I want to reiterate that most people believe that models are using observations uh, when in majority of the cases models are simulating emissions to concentration in a free flow manner, but there are times when you use models and observations, assimilate them, and come up with an improved um, pollutant distribution, which you can then use for your exposure assessment or your impacts on ecosystems or agriculture and all. And you can read about the technique and all on the source provided here and also in the reading material. Okay. And like I said, satellite alone cannot give you say compounds because satellite measures AOD, but you are interested in PM 2.5. So AOD is your how much light that an aerosol or a particulate obstructs before it reaches the ground, right? Whereas what we need is say PM 2.5 is what's needed for your health impact or impacts on your ecosystems, and that's not what satellite is measuring. And this is why you need model and satellite to come up with improved estimates of PM 2.5, right? And you cannot do it only by satellite, is what I'm trying to say. Another example, again, right off the bat, is you have what's called inverse modeling. You run the model forward in time, you look at it with observations, and then you have mathematical techniques that you use to go back in time and say how should the emissions be to better reflect the observed behavior, and that's called inverse modeling. So here, if you look at here's a paper by Wang and colleagues that they inverted emissions in China. And if you look at this was the first model emissions, and then they simulate in time, and then using inverse modeling, this was how it looked at. And again, they did a lot more observations, but I only show 5 or 6 here in this slide so that you can actually see the figures. So the initial field was blue when you're running free flow first, and then once you run inverse modeling, your observations are in red, and the inverted emissions are closer to observations. And then that helps you also estimate how good are your emissions inventory, or what should the emissions be to better match observations. So again, the models are used to invert your emissions. You get a better sense of emissions, or where your hidden emissions or unaccounted emissions, and also improve your emissions inventory based on the horizontal and temporal pollutant distribution. Okay, as I mentioned, one of the main strength with air pollution model is you can forecast what the pollution is going to be like, say, in future, which your observations alone or satellite data alone cannot provide. So here is an example of Wacom forecast run out of NCAR for PM 2.5 for tomorrow at 0Z. And not just PM 2.5, you can do forecasts for all variables that models simulate. and you can have forecasts for different times, and different days. Again, usually the forecast is done only for few days out in time, just given the uncertainty with meteorology and just the complexity of predicting pollution later than several days out in future. But again, there are different models. There's the Copernicus system out of Europe. There's in a lot of countries again provide air pollution forecasts that you can access the data or the fields to manage your air pollution and you be better prepared based on the model forecast. I'm not sure how good the simulation is coming at your end, but models, another strength with models is because you're simulating multiple species, multiple location, different meteorological variables. You can use the models and animations and try to understand the processes governing certain things. So here is an example of a 3D visualization of a pollution feature from Asia going all the way to North America. And this part here is your Alaska and North America. Again, the green ones are there. So here in the model, you can do things like okay, how is the say carbon monoxide from China, lifting, and how is it mixing with biomass burning from Southeast Asia, which is in your blue color, or say dust being blown up from the Taklamakan or the Middle Eastern deserts. How are they being lifted? How are they being transported? And how are they being removed? These white fields are your clouds. The arrows are wind fields at 2.5 kilometer, and you can have these wind fields up or down. Again, the point is models help you in sometimes seeing it's better, it's easier to understand the process or internalize what's happening. So models provide you, and you can do this replay or future or hindcast or like in past. So the strength of the model is you can understand how is the pollutant erupting, being transported and being removed from atmosphere just by plain visualization. And that's something you can only do with models. Another thing with models, again, I mean, you're trying to link emissions to concentration. And here's an example of looking at, say, carbon monoxide for a certain time of the year. So on the left panel is your total carbon monoxide. But then, I'm sitting in Nepal and, I want to know whether pollution from South India actually influences pollution over or Nepal, or if I'm measuring pollution there, was it influenced by South India? And in the model world, you can play all these games, and you can simulate only with South Indian emissions and see where this plume is. Whereas in observations, you're only able to um, measure the total CO, and you cannot really separate it out from where it is coming. So one of the main thing advantage of models again for air quality management is trying to look at um, region, sector, and temporal. Um, where is the pollutant coming from? And so this is a strong advantage that models have compared to satellite and other in situ observations. Again, here's an example of a sectoral contribution, and I could have animated this, but just so that you focus. So we were doing this project a few years back, trying to look at pollution reaching the Arctic Circle, and here we're simulating okay how much of the California fires influence pollution being measured in the Arctic area. So you can run simulations only with emissions from North American biomass burning for carbon monoxide. Right. Similarly, at the same time, you can also have simulations that look at do the smelters in Northern Europe influence pollution, observation of pollutants in the Arctic Circle. And so here are large smelters in Northern America, Northern Europe, that contribute to observed SO2 over the Arctic Circle. And again, I mean, this is very powerful in terms of air quality management because now you can separate different species, different regions, different sector, and by sector meaning whether it's coming from power plants or biomass burning, that sort of thing, right? Again, I mean, not just in 2D dimension, but here's the example, and this is using ChemX model run by Urban Emissions and Dr. Saraswati Gunda in India. You can take any location within a model. In this case, I'm showing example from Delhi, and you can extract data for any given time. So here, current today, tomorrow, and past few days, where are these pollutants coming from? Whether it's from passenger freight vehicles, passenger vehicles, open waste burning, what is their share? How is that changing on temporal scale? You know, and then again, this is the boundary condition I was talking about. Even in Delhi, what are things coming outside of Delhi? You know, what are things within? What are the contribution from residential? Or urban dust? you know, or transport. And these are things that you can use for 3D model so that you have better understanding of the pollutant, observed pollutant at your location, say some location in Delhi, and try to understand what you need to control or when you need to control. Again, if you look at the temporal distribution, sometimes it's high, sometimes it's low. What was contributing to this high pollutant loading? What are the dominant sources during this time? And then where is it coming from? Again, it's kind of source apportionment that you do using modeled fields. Same thing again, not just 2D distribution or say a megacity, but you can also use these models at any random receptor location. And here I'm showing an example of an observation that was running at the base camp of Everest. Here's the peak of Everest, and there's observations going on here. And when you observe high pollution at this location and with no nearby sources around, how do you interpret where these pollution are coming from and from which sectors? And the only way you can really get a handle on, or at least get an estimate, is to run models with region tagged or source tagged tracers, we call them. And we can have models for this period in the pre-monsoon, based on model fields. You can say how much of it was coming from, say, within Nepal or Bangladesh, India, and not just for CO, but then you can also look at the sectors, for different sulfate or black carbon organics. Where is it coming from? Which sector? Which pollutant? And the temporal distribution. And this is something that air pollution model is the only way, despite all its uncertainty, give you some sort of indication um, where the pollution is coming from. And again, the caveat is, for the model to perform well, you need to have good emissions inventory, and then also need to think about the metrology and the processes that you're simulating. Because if you're trying to simulate area like this, of course, it's not just emissions inventory that matter, but then how do you simulate your mountain winds? Do you is your model able to capture valley winds, thermal upslope, down valley winds? Does your model have deposition over these rough terrains, those sort of things? But given that your model performs adequate for or is fit for purpose, then you can use models to try to interpret observations. Okay, here's another example of where models provide useful information. They may not always be right on the dot on top of observations and all. And here's the example of how you use the model despite uncertainties. Okay. So the red dot here is observations of aerosol optical depth. Okay. And the blue dots are the model fields. Okay. And as you can see, okay, the model is in the ballpark, and then model also does elevated AOD when observations show, although model is a lot lower in observation than observations. Okay. So given the strength, of course it's not perfect, but how does it help us? If you look at observation, so now forget the model bit for now, just look at red dots. And we all know that AOD is a proxy for your particulates. And if you look at the peak time period, it's during monsoon. And those of us in South Asia or even East Asia, that during monsoon, your particulates get washed out, and you have very clean conditions because of the rainout. But guess what? The pollution high AOD is over the monsoon time period. How do you interpret these observations? Right? So one way, given despite its uncertainty with the model, you can use the model to look at what's happening during that time period. And as you can see, this is above ground, right? So here is, even though this station is at 5,000 meters altitude, this is where 5,000 meters is in the model, and then 1,000 is 1,000 above that station height, which we call the above ground layer. And you can see during that time period you have elevated aerosol layers, because you have low values here, high values in the elevated here layers here of dust and sulfate. So what the observations in showing these elevated AOD is because you have elevated aerosol layers that are being measured by observations and also put in by the model. So again, here's an example. Despite the model not being perfectly able to replicate observations, is a useful tool in trying to interpret observations. Of course, it cannot always help you interpret, but sometimes model does help you put in perspective. And this is why we say, is the model fit for purpose? And does it provide useful information sometimes? Here is another example of interpretation of the model despite uncertainty. Again, the same thing. Red is your observation, model field is in blue. And as you can see, for the time period simulated, this is in Lumbini, along the Indo-Gangetic plains here at a station and measuring carbon monoxide. Okay. So on the top figure, just notice that both the model and observation are in the same units, and model does okay at certain times and then misses these peaks. So now we want to understand where these peaks are coming from, and why is the model missing them. So while we are trying to improve the model, it also provides one interpretation, may not be the only one or the most accurate one, but one interpretation that you look at model biomass. This is total CO including biomass, where if you look at only the model biomass, if you look at the model peak, they match with the peaks that are missed by the model here. So what this tells me as a modeler is that one way to improve model performance to capture here is that I need to improve my model biomass CO. Is it good? I want to further examine that. This is for model improvement, but how does it help interpretation? At least in the model world, if your metrology is right, these pollutant peaks were due to biomass burning events that the model could not capture. Again, one interpretation that helps you put into observations in perspective. Again, there's lots of uncertainty, but if you didn't have a model, you have no idea why you have certain peaks here and certain lower peaks here, and no, is it only due to meteorology? Is there emissions at play? And that sort of thing. So example of models, despite their uncertainty, providing useful information. Now, given that your model is good or adequate or fit for purpose, what can you do with model fields? You have your 2D fields like I showed you early on. But what can you do with this? So you can take these model fields, use again your spatially aggregated population database, and then come up with things like what percentage of people are exposed to PM 2.5 greater than your WHO guideline, or you can do your own health impact kind of studies, or if you look at, say, exposure, one of the tools that are widely used globally, developed by EPA, it's called a model called BenMap, you know. And one of the primary inputs to the model, BenMap model, is fields that come from an air quality model, such as here. Of course, you have your other variables, but this is a field that needs to be put in so that you can look at your health impact functions, health endpoint, and the costs and whatnot. So model air quality models provide you with the data to run models and estimates for health exposure. Um, Here's an example of a model providing inputs to weather. We forecast weather using weather models, but then there are models that couple weather and chemistry together. And here's an example of rainfall as predicted by the TRIM satellite. Here's rainfall for the same time and space predicted by just the weather model. And here's forecast when you take into account feedback of chemistry and pollution into weather. Okay, and as aerosols and pollutants also influence weather and climate. So here's the difference between rainfall predicted by just running weather models and weather rainfall predicted by taking into account chemistry. Okay, and for this space and time and all, you can see the rainfall pattern changing up to 30-40 millimeters for that day or for that event, based on whether you have aerosol or not in your model. Which one is better? Again, I mean, you can read the papers and all, or strength and weakness, but just to show you that these are also now beginning to be used in air pollution, weather, climate models. Here is another example of how these pollutants influence your weather variables, such as humidity, your temperature at surface, your boundary layer height. In terms of here, the example here shown is how does open biomass burning, your crop residue burning in Punjab, impact your local weather in that region during that time period. Okay. And the model provides you, I mean, there's no way to validate this because model only observations only measure the current observations. It cannot say whether it's due to open biomass burning or not open biomass burning, that sort of thing. But model is the only way to give you a estimate of how much these pollutants are influencing your weather. And you can read the details on the paper there. Here is an example of model fields that are fed in to climate models. So here in the data flow chart here, the regional transport model is simulating the aerosol and trace gas fields, which then goes into your radiative transfer model. And then, then you get estimates of your radiative forcing at the top of atmosphere or surface, which then can be used for impacts on your temperature and other variables on a climatic scale. So again, Usually climate models do this on their own, but if you want to focus on a regional area or want to run a regional climate and you want better prescribed pollutant fields, then you use a CTM to constrain your aerosol so that you can run the radiative transfer model as compared to just running the climate model. Okay, here's an example of how you would use a CTM produced field to do assessment on ecosystem damage or your agriculture yield or loss of yield. So the paper by Sachin and team first simulated ozone over India, okay, and then they corrected for the model deficiency and all, and then based on the two-dimensional ozone fields, then they looked at agriculture over India, agriculture fields and all, and then came up with, what are the loss in, say, wheat yield or cotton or rice. And you can read the paper, but they've estimated not just the actual yield, kilotons per grid, but for different compounds due to say elevated ozone over India, and then how that relates to how much food is lost that you could actually feed your citizens. Okay. And again, to do estimates like this in space and time, you would still need model field, although you could also do it with observations, but then observations are too few and sparse. And to get a national aggregate, a model is one way to do the estimate. Here is an example of a model being used as a decision support tool, taking air pollution, climate, SDGs. So you want to look at, say, here's the emissions inventory for biofuel being used in Asia, and this kind of old result. But anyways, just for example, this is where biofuels are used. What happens if, from climate perspective or from SDG perspective, you take all the biofuels out and move them to a higher or a tier energy usage or a cleaner cooking? And in this case, suppose if you replace all biofuels with electricity, what is the observed AOD with and without biofuels, which has implications to your climate as well as your air quality. So you can use CTMs to come up with, estimated climate or air quality benefit. And I think this is my last slide, but let me explain this. And this is an example of how you would use a air quality model before you actually implement certain policies, or you look at what if scenarios that I mentioned earlier. Okay, so on the left here again, this is a case study from Lumbini for carbon monoxide. The red are your observations, your green is your model field. So it gives you an indication of how good the model is in terms of its capability in predicting observations. Okay, as I mentioned, it's not able to capture these biomass observations that capture the biomass plumes. On here, we can play the games as in, what would happen, suppose if you're a city planner here in Lumbini. Okay, you want to look at, okay, what would happen if I go and make that all CO within Lumbini and the surrounding grid cells within the model world in Lumbini, make them zero. Transport is electric. You have all cooking is electric. That's a sort of thing. So you make CO zero. Okay, so this is what it is saying. If you make zero, this is the 100%. This is what the green line is showing. Okay, so as a planner, if you say I want to eliminate all these emissions, what would be the concentration fields like? Okay, So here, the model is showing that it's not going down to 0 or even 20%. Why? Because you're making your reductions only within your city or your grid or surrounding grid. But then this site is influenced by regional transport, so that even if you make 0, in this case for CO, you're still going to get 80 or 90% of the observations here. Same thing, what if your emissions are wrong? And you have underestimated emissions here as much like 5 times. you know what if your emissions were wrong, and you multiply those emissions like 5 times in your model? Well, it's not going up to 500. No, because again, the same thing. Your emissions are quickly taken away, transported away, and or diffused into other areas, so that you don't get a 500% increase even for a primary pollutant like carbon monoxide. You know. So these are things that you can play, modeled simulation games or experiments, and reducing certain pollutant by this, emissions by X amount or X percentage, or that sort of thing. So is a very useful tool. Again, despite uncertainties, it gives you an indication or an estimate. For example, say the odd even rule in Delhi. Before you actually implement, you can actually run the model and see how much reductions are expected, and then implement the odd even rule. Right. Same thing, suppose you want to phase out all the diesel vehicles more than say 20 years old. You know, if you put it in the model and simulate, how much of the reductions are you actually going to expect? Despite all the uncertainties and all, you can have a first order estimate and, understanding before you actually implement policies. So again, with this, I end my talk. Of course, there's a lot more applications, but then you have to go into the details of the model in terms of physics, chemistry, and the math for its application. But from a air quality management, from a city planner, from a policy perspective, these are some of the things that you can use models for planning and management perspective. And I'm happy to take questions. Thanks.
Thank you, Dr. Adhikari, for your nice presentation on the application of chemical transport models and photochemical models, the uses in the air quality management. It was very informative presentation with full of new information and knowledge. So may I request the participants to write your questions on the Q&A box, and I will pass your questions to Dr. Adhikari for the answer. There's already a questions. So the first question is what are the major interferences for the AOD measurement, and how to distinguish PM 2.5 from those interferences?
Okay, I'm not sure if I fully understand the question, but let me repeat
It's
what I
something
think.
like interferences for the AOD measurements and how it distinguishes from the PM 2.5. Maybe direct derivation of PM 2.5 from AOD. So
Yeah,
how
yeah.
the
So, yeah.
interferences?
So again, like I said, I think there are two questions here, even though it's in one. One is, how do you actually calculate AOD based on satellite or ground-based or even model? Um, AOD is, if you look at, what AOD is, it's aerosol optical depth. It's the attenuation of light reaching from a source to receptor or like the ground. How much of that light is being attenuated by the particle? So AOD depends on the particle size, the composition, the water uptake by the particle, and because you're looking at your absorbance, reflectance, scattering, that sort of thing. So you need to think about all these. Whereas PM 2.5, again, if you look at PM 2.5, That's just the total, because PM particulate matter is composed of sulfate, nitrate, your carbonaceous aerosols, and these have different properties. So what you're measuring with satellite or ground-based is the total aerosol optical attenuation, or the depth, right? What you need, or what you're interested, is either the number concentration, how many number of particles that you are breathing, or what is the mass of the particle that you are measuring, right? So from going from light attenuation to mass and number, you need to have certain assumptions and certain theoretical framework to convert to that. And there's uncertainties on both, on AOD measurements as well as conversion from AOD to PM 2.5 mass or number. Hopefully I answered that.
Yeah. Um, there is one more question. Are some good quality uh, are some good quality air pollution models software available for free of cost?
Yeah, so the models that I was showing examples are all free. WorfCam is free, CMAC is free. Um, I think MX is also free. There may be licensed versions as well, but most of the air quality models are openly available. And as I mentioned, I think for a beginner, rather than trying to run the models by themselves, I would urge you to look at model fields that are freely available, model data that's available. Try to understand, their applications before running your own model. But yeah, in short, yes, there are several models that are freely available, including software requirements, compiler requirements, and uh, just the licensing requirements.
Yeah. Uh, the differences between observation and model output, does it indicate that the emissions used in the models is underestimated?
Again, I mean, see, this is the issue that why I refer back to the data flowchart in both presentation is, uncertainties can come from anywhere. You there are uncertainties in your inherent processes, uncertainties in reaction schemes, uncertainty in deposition, uncertainty in your emissions, uncertainty in metrology. So again, depends the time space application that you're looking at, and it's not always emissions, although that's one of the major reason, but again, emissions are only one source of uncertainty for the models, but not the only one or not the only one.
Okay. There is another question to uh, what is the difference between CMAC and CMAX?
CMAC and
CMAC and CMAX, CAMAQ, CAMX.
CAMX. Okay,
CMAC and
CAMX.
CMAX, yeah.
Okay, again, like I said, if you think about the first talk, okay, models are different based on the physics, chemistry, math that they use. Okay, so like say one model might use finite differencing to compute, say, certain process. Another model might use another mathematical technique. One model might use, say, Bradham chemical mechanism. Other might use Saprak mechanism. So depending on the individual processes that models are simulating, that's how they are different. And also in terms of usage, like say for example in US, WRFChem is used by community to look at weather, climate, and understanding atmospheric processes mostly, whereas CMAC is the model developed by EPA and approved by EPA for regulatory purposes. Doesn't mean anyone is better than the other. you know um, it's just that certain models are approved by governments for regulatory purposes, or certain models are accepted by research community because it does a lot more detail. Again, depends on the application that you use and the purpose that you're using models for. In terms of general air quality management, all models are good, all models are bad. Again, depending on the emissions, depending on the input that you give, processes that you're trying to simulate at a scale, temporal or spatial resolution. And again, like I said, I think a lot of people that do not run models are too stuck up with, oh, models are uncertain or we don't have this. And the point that I was trying to show here is, yes, models are imperfect, period. But can they provide you with some useful information that observations in satellite cannot provide? So, you want to use these model from that perspective, not as a authoritative source or a Bible in that sense, or or a you know the first principles kind of, okay, this is what it is. You need to take model fields and interpret it accordingly to the case that you're analyzing.
Yes, the last question, before we are running out of the time, but it looks quite important questions. How do you link regulatory air quality models, that is CalPUP, with regional models?
Again, I'm not familiar. I mean, I did very early on in my undergrad days, but I'm not sure if we do link them. And again, the CalPUF and your AirMod and your dispersion models are your 2D models that look at a particular source and then disperse the pollutants um downwind. Whereas your regional air quality models are looking at space and time, where you have multiple sources, multiple sectors, multiple pollutants. So they're really different models, and I'm not quite sure what you mean by linking them together. You can use
Okay.
both to try to understand, but there are different questions that they're answering.
Yeah. You are really running out the time. So thank you so much, Dr. Adhikari, for your very, very nice presentation. And thank you so much for giving time to this workshop. And thank you for your contribution to workshop. Now
Thank you,
the
Dr. Verma. And
yeah,
let me use this time to say thank you to AIT for inviting me as a resource person. And I hope the talk was useful, and I'm happy to answer any questions that you may have. Please send the email to Dr. Verma or directly to me. And as Dr. Verma mentioned, the PDFs are uploaded. Please feel free to go back to them and get back to me with any questions. So thank you, Dr. Verma and AIT for inviting me.
thank you. Thank you so much. Now the last and third presentation of the day on module 3 is uh, on air quality forecasting with focus on PF 2.5, and this presentation is by Dr. Sakada Tridej from the Pollution Control Department, Government of Thailand. Dr. Sakada is an environmental senior professional level and a director of Air Quality Model and Geographic Information Center at the Pollution Control Department, the Ministry of Natural Resources and Environment, the Government of Thailand. He received his PhD degree from Brunel University in 2012. Dr. Tridej, the floor is yours. Thank you so much for joining.
Thank you very much, Dr. Verma. All of you guys can hear me clearly?
Yeah, we can hear you.
Okay, thank you very much. So, okay, first of all, I going to share my presentation. Okay. Okay, can you see my presentation now?
Yeah, we can see. Can you make it big?
Okay, okay, let's go.
Yeah, that's great. Thank you so much.
Okay, so I can begin now. Okay, So I think all of audience, as I see from the program, I guess all of the audience come from the ASEAN group. So may I say?
No, Dr. Sekda, sorry. The participants are from all over Asia, South
Oh,
Asia, Southeast Asia, even beyond the Asian countries. So
okay.
more than 30 countries are joining the workshop.
Okay. Sorry, I misunderstood. Sorry. Okay. So the topic that I'm going to share today is a comprehensive concept of a PM 2.5 forecast, a case study in Thailand. So because I know from the administrator that there's a diversify of a group of the audience. Some of you might be an expert, and some of you might be an beginner who interested in to use the air quality model. So then I prepare my presentation for both group, for the group of a beginner that who might interested in well, how to use the air quality model for your work. And I'm going to show some of the product from the pollution control department Thailand that we use in terms of forecasting for PM 2.5 to cope with our critical problem. Okay, so first of all, I would like to introduce myself for a little, just a little. Most out of my degree, I graduated in manufacturing engineer. So what I would like to say that I would like to inform all of you guys that at the beginning, I don't have background in the environmental, but I have a background in some of mathematical and computer programming. So what I would like to imply, I mean that if you have a basic of a mathematical and some basic of computer programming, yes, you can use the air quality model. Okay, so this is the contents of my presentation today. First of the first, I would like to share the information to all of you guys that the basics of air quality models. Then we are going to discuss the essential basic needs. What is the essential that you need to know first before you're going to use the air quality models? And then the third topic that the background of a PM 2.5 problem in Thailand, that the case study that I would like to show you how's the problem in Thailand and how we are going to deal with this problem. And then we will move to the chemical transport model. And between this topic, I'm going to show you why we choose to use a chemical transport model as a tool to cope with the problem in Thailand. And then uh, the main tool that I will show you as a chemical transport model is a WRF-CAP. And then I'm going to show what is the requirement if you would like to use a WRF-CAP as a air quality model. And then just to discuss that just a little bit what model configuration and input data. And so the last thing, I will show you the product example that I did the simulation last season in Thailand. And then we'll show just a little bit of some evaluation of a model versus observation data. Okay, this is all of the contents that we are going to share in this lecture. Okay, I have 50 minutes left. Okay. First of all, this is just for the beginner who is interested in to use the air quality model. I think all of you guys may heard some kind of the name of a model like WRF-CAM, CMAC, CAMEX, even AirMod or the CalPAP, but also PMF and yes, okay, but you have to clear more clearly that what is the type of these two? What is the type of a model? I recommend you that you guys to go to the US EPA website. This is more clearly. This US EPA can clearly categorize the kind of the category of air quality model. I'm going to say that in the all of air quality model, there are three types of air quality model. First of all is dispersion modeling. Dispersion modeling, what does it mean, or what is referred to? Normally, this kind of model is used to simulate concentration of pollutant as a specified ground level. This is a dispersion modeling. And the second one is photochemical modeling. Yes, the name of photochemical modeling is just clearly is used to simulate chemically active pollutant over large spatial scale. And the last one is receptor modeling. It's used to quantify source contributes to the receptor concentration. Okay, and from this point of view, dispersion modeling. Okay, the basic of this model, you may familiar with the name of AMOD, steady state plume model. This is a basic dispersion model. And what is a photochemical modeling? As CAMEX and CMAC and even Wolfram. What is the different vast difference between these two models? Dispersion modeling, you have to bear in mind that no chemical reaction. If I mention in the AMOD has a constant of like many parameter, emission rate, and some parameter of weather condition, meteorological condition. You can use basis on what is the objective of your work, like permission work or environmental impact assessment. Because I will show you some example in Thailand in environmental impact assessment. In Thailand, we indicate that we approve to use AMOD in terms of EIA assessment. But like I mentioned before, you have to bear in mind that AMOD or the basic dispersion modeling, this kind of tool does not have a chemical reaction in this tool. So when you use, you have to keep this in mind. Okay, so we are going to photochemical modeling. These two have a chemical reaction in atmosphere. But if you might think in your mind that, okay, these two have a chemical reaction, but dispersion modeling does not have. Why don't we skip to use photochemical modeling instead of dispersion modeling? Because photochemical modeling, one of the major thing that is very complex and complicated in the setup, and it depends on the objective of your work. And then the receptor modeling, this is like I said, is like a PMF model to use to quantify the source contribution at the receptor concentration. So in my presentation, I'm going to discuss both specifically on this dispersion modeling and photochemical modeling. Okay, so I got this picture from a source of a website. I will indicate the source of the website in the last part of my presentation as a reference. I would like to share with the beginner. You have to understand that even dispersion modeling or even the photochemical modeling, the objective of using air quality modeling is to determine the concentration of interested air pollutant at receptor point. And what do we need to input as a basic in this in air quality modeling? Three things. First, the emission rate of a pollution source. The second one is the meteorological data. And the third one, and the last thing is the geographical data. So if you have these three inputs, you can make a simulation, even the basic tool or even the complex tools. So for the beginner, you have to clarify what is the concentration, is the unit of mass per volume. What is the emission rate, is the unit of mass per time. So you have to understand this one first. And then, as I show you this figure, if you would like to use an air quality model, so you have to have some basic of meteorological, and you have to have some basic of geographics or coordinating system. So let's move to the next one. Okay, so this topic is the essential basic needs. Some of you might familiar with the term of inversion, temporal temperature inversion. So in the scope of air quality model, the meteorological condition is quite very important, because I think you may familiar that when we enter to winter period, we have the same activity, same loading of the traffic, and the factory operating in the same scale over the year. But why in the warmer or in the sunny time or in a warmer period, we don't see some the problem. But when we move to winter period, we will see some problem occur. Let's say in the case of Thailand, when we move from the summer times to winter time, let's say in November and December, January, and February, both Bangkok and metropolitan, and also northern part of Thailand, we suffer a PM2.5 and also PM10 problem. Why? This is a very important. I show you the left hand side. This is some normal situation. Normally, warm air is near the ground level, and when the altitude increase, the temperature will getting cold. But when you see the right hand side, when the warm layer is between cold layer in the ground and cold layer above the warmer air that in the middle. This is the situation of inversion. And why the inversion effect? That's I mentioned you. Okay, let's see this one. Normally, when we have a warmer layer near the ground level, the air parcel can rising up in the vertical, and we will have the horizontal air pass through it. This will call the mixing process. Will keep air refresh. But when you see the bigger picture, when the high pressure dominate the situation, and we got the inversion, so the inversion can form the fog. And what happened? So when we have the source of pollution, let's say the traffic, open burning or factory, so the air pollution can be trapped near the ground level. The mixing process cannot happen. So this is why we should know the process of the weather condition, or even the important meteorological parameter. So I put the source of this figure. Actually, it's the video from National Weather Service, NOAA. Last 2 years, I got the license from National Weather Service NOAA to use this video for the education for people of Thailand. So I would like to share this video to all of you as well. So as I told you, the meteorological condition is quite very important related to estimate the situation of air pollution. So let's say in terms of forecasting, or in terms of the government planning, how can we deal with this problem? How can we know what's gonna happen when it's gonna happen? The season that can happen, when and where. So today we have numeric modeling called WRF, Weather Research Forecast Model. This is a very useful model that I suggest all of you guys, if you have interested to use air quality model. You may have to understand these two as well. The Weather Research Forecast Model, you can use this to forecast many important weather condition. Let's say like wind speed, wind direction, planetary boundary layer, lift index, or even CAPE, convective available potential energy, and even the rainfall. So this kind of tool is very useful. But in my presentation, in the next in the next part, I'm going to share with you. If you would like to use the WRF, what do you need if you would like to use this kind of tool? This is some of my simulation that I use in my work last year. I every day as a routine work, I predict weather condition in both part of Thailand, in Bangkok metropolitan and also in northern part of Thailand. The critical parameter that I suggest you, if you're interested in to learn how to use the weather condition combining with the air pollution forecast. The first thing is the planetary PBL, planetary boundary layer. What is the PBL? PBL is the lower part of a troposphere layer. If I say in the easier definition, it's like a ceiling of our room. I last around 8 years before, I have a chance to study with Mr. Stephen Beckham. He is one of a developer of a WebCam team. He teach me that you have to understand PPL because if you close your eye and imagine that you have a room and you have a one spot of a fire in your room. The lower ceiling of your room and the higher ceiling of your room, you will feel the difference of concentration of smoke in the room, because the higher ceiling you will feel more comfortable, but the lower ceiling in the room you will feel uncomfortable, or in the other term it means more concentration of a fire in the room if you have a lower ceiling. So PBL, if it has a unit of meters. So what does it mean, and what I'm going to imply? The PBL level has different level in different season. So this is a very important parameter if you're going to use the air quality model to forecast or to estimate air pollution in the intersection area. And the other thing, the other parameter is the convective available potential energy, CAPE. So if you have a more higher CAPE, higher CAPE, the rising of air parcel is quite well. So this is quite important parameter that you have to know as well. And one more thing, the third one is the lift index. And the last one is the wind speed. As I mentioned in the previous slide, the mixing process, we depending on the wind. So so the higher wind speed is more better. Okay. So this is just example of a weather condition that I recommend you guys to get familiar for the beginner. Okay, so let's move on to the other presentation. Okay, this is a third one of the essential basic needs that you may have to familiar with if you would like to use the air quality model. Most of the air quality models, it will simulate or calculate the results in terms of a grid base. What does it mean of a grid base? As I show you this figure, air quality model will simulate or estimate the interested air pollutant in every grid that you indicate. So what does it mean? Okay, so if I have a domain, my domain is Thailand, the country of Thailand, and I indicate my model for 4 grid. Oh, do you think this is realistic in the real world if I have just only 4 grid? So if I have a 4 grid, maybe Bangkok and Rayong province in the east part of the Thailand have a same simulated result of a PM 2.5. Is it realistic? No, not realistic. So what does it mean? If we have more grid in our domain, is it realistic? Is it better? Yeah, it is a high resolution. But what is the best resolution that we're gonna use? This is this question last 8 years. I also did ask Stephen Beckham, what is the best one to do to indicate the grid for air quality model? The answer is, he told me that it depends on the objective of your simulation. And the one more thing that very important, that it depends on your equipment or your workstation, because out of the air quality model, if you indicate very high resolution or many grids, your workstation will get a lot of work, and it results in the long time run. For example, I used my workstation at PCD, Pollution Control Department, Thailand. My first workstation has 40 cores, and I did run the simulation for resolution 3 kilometers, forecast for 24 hours. It take 12 hours to finish. 12 hours to finish, just only one scenario, 24 hour forecast. So is it work, or is it good for routine operation? And the answer is definitely not. So if you are going to design your domain for air quality model or your work, you have to bear in mind that what is the best resolution for your work and your objective. Okay, but before you go into decide that, you have to understand some basic of geographic information system, or even Earth coordinate system. So this is very essential for the beginner. Okay, the one more thing of essential basic needs that you need. I change my word. You must know before you going to use your air quality model, specifically or photochemical model. You have to know some basic of chemical reaction in atmosphere. Why? Because you might familiar with the term of primary pollutant and the term of secondary pollutants. The primary pollutant is directly emit from the source of pollution. Maybe factory, maybe a household, maybe open burning, and maybe agriculture, or even the transport. The primary pollutant directly emit from source of pollutant into atmosphere. But when this primary pollutant emit into atmosphere, it can react in atmosphere and transform into secondary pollutant. In this part of my presentation, I will focus on the PM 2.5. As I think all of you might know that PM 2.5 have major source from like NOx, sulfur dioxide, and BC and OC. So NOx and sulfur dioxide most come from like a power plant, and come from diesel combustion engine. And when it emits from the source into the atmosphere, it can be react with ozone in the atmosphere, and even catalyzed by solar radiation, and transform, and also black carbon and organic carbon as well. So if you would like to use chemical modules, let's say CMAC, CAMEX, or WAFCAM, you have to know this theory well. So all of these essential basic needs, I would like to repeat one more time. With weather condition and meteorological data, you have to familiar with this one. Geographic information system and Earth coordinate system, and the last one is chemical reaction in atmosphere. So this is essential basic needs that you need to know. So this is a very interesting that I would like to share with you. So that's why in now today when we discuss that how can we control the situation of PM2.5. So that's why we have to control SOx, NOx, and control soot of dust emission. So this is what it coming from when we talk about how to control the PM2.5 situation. Okay, so let's move on to the next topic. Okay, I have 25 minutes left. Okay, this is a case study that I mentioned in the content first. This is a case study in Thailand. In Thailand, we suffer the situation of PM2.5 problem in winter period. We have four critical area. First one is the BMR, Bangkok Metropolitan, and the second one is the northern part of Thailand, and the third one is the Suraburi province and also the Rayong province. Okay, and source of the problem, as I mentioned you before, is coming from industrial pollution, transportation, and also the burning area. So this is the basic information that we know in our country. And in last year, the National Environmental Board of Thailand, under the Royal Thai Government of Thailand, we established the Center for Air Pollution Mitigation, or CAPM, and we have Director General of Pollution Control Department as the administrator. Okay, and the important mission of the CAPM is the number 7. We have to forecast PM2.5 in advance for 3 days. So we have to find out the best tool to serve this mission. So we select to use the chemical transport model. So as I mentioned you before, what kind of a tool, dispersion model and photochemical model, and what is the limitation of a basic dispersion model, and what is the source of PM2.5. So this is why the reason that we choose a chemical transport model, because if we would like to cope or mitigate the PM2.5 problem, we cannot just only use the steady state plume model, or we cannot just use the basic dispersion model, because it does not have chemical reaction or chemical module in the tool. So that's why this is the reason that for the Pollution Control Department Thailand, we select to use the chemical transport module to deal with the PM2.5 problem. So this is a good layout to illustrate what is the chemical transport model formulated. In chemical transport model, we have two major elements. The first one is the numerical vessel prediction model. Like I said, WRF model, and also the chemical transport model that involve the chemical aerosol diffusion and transport module. So if we have two elements in this chemical transport model, we can do the forecast of a PM2.5 situation. Both of a WorldChem and CMAC and even a Chemex can do this procedure. Okay, so this for this part, as I mentioned you in my content of my presentation, for the beginner and for the user who interested in to use the WorldChem system, what do you need to have if you would like to use this kind of tool? I have 3 major things that if you would like to use. this kind of two. The first one is the middle column of this presentation, OS or operating system. You have to bear in mind that the major thing that this kind of tool, it is not operating on Windows-based system. It operating on Unix-based system. You may familiar in terms of Linux or Ubuntu, CentOS or Red Hat. You have to operate on this system, not Windows-based system. And the left-hand side column, when you would like to install WebCam or CMake or even CAMX in your system, it is not like a Windows-based system that you insert a CD-ROM or DVD-ROM and you find you're looking at for execution file and just click next. No, you have to compile the mathematical model using the compiler. So you have to have your compiler in your system. And in nowadays, there are many kinds of a compiler, even free compiler and even commercial compiler. In pollution control department, we use the GNU GNU compiler because it's free. But in pollution control department, the major workstation we use at the other place. It's we use the workstation at the NASA Supercomputer Center. At NASA Supercomputer Center, it uses the compiler Intel compiler. This is a quite important thing that I would like to suggest you guys, because different compiler sometimes return a bit different simulation result. So you have to bear in mind if you have the chance to use the kind of compiler. Just so you have to beware this factor as well. And the last thing is a workstation. As I told you before, this kind of tool, WebCam, CMake, or CAMX, you cannot just use the ordinary workstation. I will let's say last 8 years when I have a chance to learn to use a WebCam with Stephen Beckham. He asked me that what is your can you show me what is the configuration of your workstation? I told him with my confidence that, oh, my workstation is the Core i7. He laughed on me and he said, oh, so funny. You cannot use that workstation to run WebCam. At that time, I don't understand why I cannot use the Intel Core i7 to run the simulation for WebCam. So when I come back to Thailand and I set up my simulation, and it takes, let's say 12 hours or almost 24 hours. So I understand, okay, it takes a lot of workstation resource. So you have to, if you would like to use this kind of tool, you have to bear in mind for this one, for the factor of the workstation, very important. So this is the workstation that pollution control department use. We use high performance computing at NASA Supercomputer Center. This workstation, as I showed in my presentation, it has 4,320 cores. So actually, for my routine works, I use just only allow 200 or maybe 250 score. So to formulate, to simulate my scenario, it takes just only 45 minutes to finish. You see, I can reduce processing time from 12 hours to 45 minutes. So if you would like to use this kind of tool and with high resolution of a grid of the results, you have to have your very powerful workstation to do it. Okay, so this is a workflow of a pollution control department. In Wolfram system, it has two major parts. It has a pre-processing part and it has the simulation part. In my routine work, I do the pre-processing part at the workstation at pollution control department, and then I transfer the input file to NASA Supercomputer Center to do the simulation job, and then just got the result and to do post-processing at pollution control department. This is a workflow of a pollution control department. Okay. Oh, I have 10 minutes left. Okay. So this is a domain configuration at the pollution control department. Then when we use for the BMR Bangkok metropolitan situation, we have three domains nesting. The master domain, we have a domain that cover all of the area of the Thailand and some area of a neighbor country. But the target domain, the third domain, the red one, okay, the grid resolution is 3 kilometers. Last 2 years before we can access to use the result at the NASA Supercomputer Center, the target domain, we can use just only 10 kilometers because we don't have enough resource or appropriated workstation. So last 2 years, we can just only did for 10 kilometers. But luckily, last year, we have a collaboration with the NASA Supercomputer Center, so we can step up from 10 kilometers to 3 kilometers. So this is the domain configuration for BMR area. Okay, and also this is the domain configuration for the northern part of Thailand. We also have 3 distinct domain as well. The matter domain is the same with the BMR. The matter domain is 30 kilometers, and the second domain is the 10 kilometers, and the third one, the target domain, is the 3 kilometers. So this is how we set up for the domain configuration to use in pollution control department. This figure, I use a graphic from the pre-processing system in the WRF system to illustrate the domain configuration. Okay, let's talk about the emission inventory or input data. The emission inventory that pollution control department Thailand we have a collaboration with King Mongkut or JTC Thailand. They produce the input data or emission inventory for us. The emission inventory they produce or cover sulfur nitrate, BCOC that important for forecasting for simulate PM 2.5, and they use the top-down approach to develop this emission inventory, and very high resolution, 1 kilometers, and the data set has the base year for 2015, but I know that they have a quite newer version. Maybe if I don't misunderstand, is 2018 for the new data set. So this is an emission inventory that we use for the like anthropogenic data for Wolfram input. And if you see this figure, you will have like a orange or yellow line. I will say that this is a most coordinate on the road network in BMR. Okay, so let's go for the next input that I would like to show. In terms of a forecast of air pollution that pollution control department use, we use input from GFS, Global Forecast System. If you use GFS Global Forecast System, you can simulate to forecast in advance maximum 16 days in advance if you use a GFS. But there is other dataset for meteorological dataset is ECMWF, but I never used it before. But my friend in Malaysia and my friend in UK suggest if I have a chance, I should try to use ECMWF. So that's why I show you. You can use both GFS or ECMWF to do your simulation. Okay, this is a model configuration. It's around 7 minutes left. So this one I maybe skip because it will go to in more detail for model configuration. I just skip to some product example that pollution control department produce to use in our. This is the some example of PM 2.5 forecast that we use in January 2020 and 2021. We can forecast PM 2.5 in advance for 3 days, and so we can know that what is the direction of the PM 2.5 movement to in which direction. So this one is very quite useful if you are interested to use. And when you finish your simulation, the one more thing that you need to concern is the post processing, the graphic that you are going to use. The last previous presentation I show you is the 2D post processing, but you can also do it in terms of 3D. It's more convenient to see the direction or the movement of the plume of a PM 2.5. So this one I show you can use a post processing for 3D animation as well. And this is the product example of a northern part of the Thailand. This one I show you. Okay, this figure, or you say many red color on the area of the northern part of Thailand. This one is 4th April, but this figure is 30 April. Same emission inventory, but different weather condition. You see, that's why I told you before. You have to understand the principle of meteorological and weather condition, because it's a very impact on your simulation. And this is our work that cooperating with the Thai meteorological department. We present this kind of a figure for the 3-day in advance forecast every day in our website. So this is our product example. So one last thing, some evaluation. I am not finished to the evaluation using statistical tool, but I just would like to show some preliminary evaluation when we use WorkCam and versus observation data. The first thing that it returns some good potential result that when the system forecast next day or next 3 days is going to have more concentration on the PM2.5 in northern part of Thailand. And when we look at the observation data, okay, it have the same trend. When it said going up, the observation go up, and when it return the simulation results is have the decrease in the concentration, the observation going down. So same trend. So okay. Okay, so the one last thing that I would like to show you, the performance of HPC that we use as a National Supercomputer Center, it returned in the good processing time. When we use 200 cores, just only 45 minutes run. But when we use our workstation, 24 core, it takes 7 hours. So that's why all of you guys need to have a good workstation if you would like to use a webcam system. Okay, so this is my last presentation. This is my future works. So in Pollution Control Department, Thailand, we try to expand the boundary of a target domain because the Director General told me that we must expand the target domain for all of the country of the Thailand. So maybe it means the target domain should be 3 kilometers or even 1 kilometer for the whole country of the Thailand, and then improve resolution and accuracy. Oh, wow! And the third one is to find the optimal solution for supporting short and long-term haze-free strategic planning. And then the one last thing is the update emission inventory. As you know, it's really, really important if you have a very update emission inventory. So it will return you a good simulation result. And this is the last slide. This is a reference that I suggest you guys if you have if you're interested to use this kind of tool, which website or which e-document that you can go to see and learn and to try to use this kind of chemical transport module or even dispersion modeling. Okay, thank you very much. Okay, I'm on time.
Thank you so much, Dr. Tidets, for your nice presentation on air pollution forecasting with focus on PM 2.5. It was very nice presentation with a lot of new informations and the knowledge, and also the how the pollution can be focusing on the PM 2.5 can be forecast using the models. Now may I request the participants to put your questions on Q&A box so that I can request Dr. TZ to answer your questions. There is a question from your experience between the northern and BMR, which region the model forecasts the best, due to which and which factor? Robust emission inventory or less complex terrain?
Okay. So for this question, I understand is the question is the when.
Okay, let me repeat again.
Okay.
From your experience between the northern and BMR, which region the model forecast the best, and due to which factors?
Okay.
Whether it's a emission inventory or less complex terrain.
Okay. Based on my experience, when we compared the BMR area and the northern part of Thailand, the model returned a good result for BMR, better than the northern part of Thailand, because the northern part of Thailand in the critical season, it has one major factor is the open burning, because the open burning is dynamic, not static. So if you don't have the dynamic input for this for the open burning, the simulation result cannot return in a good result. So that's why maybe in my plan in the next season, we plan to looking at the satellite data from Himawari satellite, because it's quite for more frequencies, and the complex for the complex terrain. Yes, the dotted part of Thailand, I think this area is much difficult when we compare to the BMR area. So my answer, hopefully, for your question, the BMR return a good simulation result when comparing to northern part of Thailand.
Yeah. There is another question. How can you create a data set of emissions for the forecast period?
Okay.
How can you create a data set for the emissions for forecast?
Okay. Okay. I will answer into 2 points. The first one is if you would like to create your emission inventory, you can use, like I said in the presentation, you can use the top-down approach to calculate your emission inventory. Maybe you can use the model like a gain model to determine your loading of your emission inventory, and then you can use the principle of a data allocation to construct your emission inventory. And the second answer for me is if you have your emission inventory and you would like to input in your model, you can do so many ways. For example, you can create your own Fortran programming to transform your emission inventory to do your own data set and to import in your air modeling. So hopefully this is useful for your question.
There is a question about the operating system. If we have a low speed computer, which operating system is best to run the model, Mac or OS or Ubuntu or Linux?
Ubuntu is okay. I recommend for the beginner to use Ubuntu, because Ubuntu has have like same user friendly like a Windows system. So if you are just a beginner, I recommend you to use Ubuntu.
How accurate the model results in Bangkok you can reach at present?
Okay, how accuracy? Okay, if let's say if we talking about in terms of if when I use a root mean square error to compare with the observation data, the accuracy is just between 50, not more than 70%, just only between 50 to 70%.
Okay. Is there constant emissions for the forecasting period?
Is there constant emission
for the forecasting period?
Is the constant emission for the
I think the question is confusing.
Yes, the constant emission. I'm not so sure I understand, or you.
Yeah.
Maybe the question is just talking about the temporal resolution, or maybe some, okay, because
maybe.
if we're talking about the temporal resolution, yes, some period we have a constant for this temporal resolution. Maybe I think this is hopeful, useful for your question. Okay.
Okay. Let me see if there is some questions. I think we do not have more questions now. So
Okay.
thank you so much, Dr. Tridej, for your presentation. It was really nice. So with that, this talk, we will come to the end of the presentation of air quality modeling module for day 3. And this is the end of this today's session of the workshop. Thank you, expert speakers, for your presentations, which were full of new information and knowledge. I believe all the participants will benefit from the information and knowledge you shared. We are really thankful for your contribution to the workshop. Thank you, participants, for joining today's session. Thank you for your interest and participation. Please join tomorrow at 1 p.m. Thailand Standard Time for the 4th session of the workshop on Module 4, that is Air Pollution Impact Assessment. We will upload the PPTs of today's presentation on the website. Please visit the workshop website for reading materials relevant to today's presentations. Also, please provide your evaluation feedback for today's session. We have already uploaded we have already provided link to the feedback form or the evaluation form to the evaluation section of the website. This is needed for the to awarding the certificate. So you may evaluate the whole workshop at the end of the workshop, but it would be great if you could provide feedback after each session. Otherwise, you will forget the contents of the presentation. Thank you again. Thank you again for participation. Have a nice evening and stay safe. See you tomorrow at 1 p.m. Bangkok Standard Time. Thank you so much.